Okay, now we'll discuss surfaces of revolution. Now, if the graph of a continuous function is revolved about a line, the resulting surface is called a surface of revolution. So here you see we have a continuous function here, continuous function, and we're revolving it around the horizontal axis of revolution. And this shape that this surface that we formed, this hollow on the inside, is a surface of revolution. And what we'll be looking at is we'll be trying to find the area of such a surface of revolution, the surface area. All right, so first we'll start off with a function y equals f of x that has a continuous derivative on the interval from a to b. That's the same criteria we had for finding the arc length. The area S, capital S this time, of a surface of revolution formed by revolving the graph of f around the horizontal axis is given by this formula, and where r of x is really the distance from the graph to the axis of revolution. So in this case, for horizontal axis of revolution, the r of x is actually just the functional value, the height of the function. And in this case, down here, we have a vertical axis of revolution, and we're going from C to D, and in this case, we have r of y. This is a function of y, not x, and it's the same. It's the distance from the axis of revolution, which in this case is vertical, to the function itself. So it's the distance from the axis of revolution to the function. All right, so let's go ahead and try to calculate the area of this surface of revolution. All right. Well, the first thing we want to do, we want to take a look at the fact that this axis of revolution, see we're revolving around the x-axis, that's a horizontal axis of revolution. So all of the functions are going to have to be in terms of x that we are going to have in our integral that defines the area here. So let's see. It looks here like we're going from 3 to about 8. So we're going to be, let's set up the integral. This integral is going to be the integral from 3 to 8. And then the first thing we'll have is the r of x. Well, the r of x is the distance from the axis of revolution all the way up to the function in this case. And that distance is just the functional values, the y value of that point right there, which is 2 times the square root of whatever the x value is. So the y value of that point is going to be my r of x, and that's 2 square roots of x. Next, well, let's see. The rest of the formula says we have the square root of 1 plus the derivative squared. Well, I forgot to calculate that, but the derivative of this, y prime, is equal to x to the negative 1/2 power. So what we have here is 1 plus x to the negative 1/2 power squared. And we're going to do this integral with respect to x. And this expression, or this integral, will give me the area of this surface of revolution. So let's go ahead and do the calculation here. Let's see. Well, one thing I can do, I can combine these two radicals to make this integral from 3 to 8 of the square root, oh, I forgot the 2, 2 times the square root of x times 1 plus x to the negative 1 power dx. And that turns into the integral from 3 to 8 of 2 times the square root, and then we can do this distribution to get x plus 1 dx. And then we are going to do this integral. I think we have enough now that we can actually calculate this integral. And this is, you can do this by u substitution, but this is really 2 times the integral from 3 to 8 of x plus 1 to the 1/2 power. And if you want to do that integral, you can let u equal x plus 1 and then do all that. And after the u sub, you will get this expression. This will be 2 times, uh, and when you integrate that with a u substitution, you get 2/3 times x plus 1 to the 3 halves power. X plus 1 to the 3 halves power. And we're taking this integral from 3 to 8. So, upon substitution, we get that this is equal to 4/3 times 8 plus 1, 8 plus 1 to the 3 halves power, minus 4/3 times 3 plus 1 to the 3 halves power. And moving down here, let's see. That turns out to be, well, 8 plus 1 is 9, and 9 to the 3 halves power is 27. So we get 4/3 times 27 minus 4/3. Well, 3 plus 1 is 4, and 4 to the 3 halves power is 8. So this integral turns out to equal 76 over 3. So the area of that surface of revolution is 76 over 3. All right. Oops. And there's one thing that I forgot for the whole problem. There's actually a 2 pi in front of the integral. So we actually have a factor of 2 pi that's been left out here. So there should be a 2 pi in front of the integral here. There should be a 2 pi in front of the integral all the way down. 2 pi. So the integral has 2 pi in front of it all the way down. So we still have a factor of 2 pi here. We have a factor of 2 pi here. And a factor of 2 pi here. So it turns out that our answer that we got should have a factor of 2 pi in it. 2 pi. So that down here, it's actually multiplied by 2 pi. And it turns out that the actual surface area is 152 over 3 multiplied by pi. So the process is correct, except I forgot the factor of 2 pi in the very beginning, so I put the factor of 2 pi here in at the end. Okay. Now let's take a look at one that has a vertical axis of revolution. Uh, let's take a look at this function right here. Y equals 9 minus x squared, which is a parabola, and we're going to try to find the area of the surface. So the first thing we want to do is we want to get everything in terms of y, because we know we're going to be using the formula where the axis of revolution is vertical. So I'm going to take the y minus 9, or y equals 9 minus x squared, and I'm going to solve it for x. So let's see, that's going to be x is equal to the square root of 9 minus y. So this is the function as a function of y as opposed to x. Then we're going to plug this in for the r of y, but we also are going to need the derivative of this. We're going to need the derivative of this with respect to y. So we're going to find x prime. X prime here is 1/2 times 9 minus y times the derivative of 9 minus y, which is negative 1. So the derivative here is negative 1/2 times 9 minus y. Okay, so now we're going to plug that in to our surface area formula to get that the surface area is equal to 2 pi, that's the one I forgot on the last example. That's the factor I forgot. Times the integral. And then we have to see where the y values start and end. The y values start at 0 and end at 9. So this is the integral from 0 to 9. And the r of y, well, that's the x values, the distance from the axis of revolution to the actual function. And in this case, that's the x value of the function because we need it to be in terms of y. Here's the x value of the function. It's the square root of 9 minus y times the square root of 1 plus, and then we're going to have the derivative squared, which is going to be negative 1 half times 9 minus y, all raised to the power of, oops, I forgot this here. This should be negative 1 half power. When we take the derivative, we have to subtract 1 from here, so we get to the negative 1 half power. So this should also be negative 1 half here. And this is all then squared. So let's erase one of these parentheses. So this is to the negative 1 half power. And this whole thing is also squared. So we're taking the derivative with respect to y, and we get this thing, which we can rewrite as 2 pi times the integral from 0 to 9. And we can take these two radicals and we can actually combine them into one big radical of 9 minus y multiplied by 1 plus, and then we can actually square this. If you square negative 1 half, you get 1/4. And if you square 9 minus y to the negative 1 half, you get 9 minus y to the negative 1 power dy. And then we can go ahead and we can distribute. Okay, now we can take this factor of 9 minus y and we can actually distribute. 9 minus y times 1 will give us 9 minus y. So we'll have the square root, we'll have 9 minus y times 1. And then we'll also have 9 minus y. Oops, when I squared this, I said 1/4, but I wrote 1 half. So this would be 1/4. When you square 1 half, you get 1/4. So let's see. This will be 9 minus y times 1, and then 9 minus y times 1/4 times 9 minus y to the negative 1 is just 1/4, because 9 minus y to the first and 9 minus y to the negative 1 just cancel each other out. So we get plus 1/4 dy, and we're still integrating from 0 to 9, and then we still have our factor of 2 pi in the front. Okay, so 9 minus y plus 1/4. Well, we can combine the 9 and the 1/4. 9 is actually 36 over 4. 36 over 4 plus 1 is 37 over 4. So 37 over 4 minus y. We still have the square root. Still doing the integral with respect to y. And we're still going from 0 to 9, and we still have the factor of 2 pi in the front. All right, so we have this expression. Now we can actually do our integral here. That integral can be done with a u substitution. If you let u equal 37 minus 4, or 37 over 4 minus y, then the derivative of that is going to equal negative dy. So we have the dy that we need. All we need is a negative. So we put a negative in, and then we put a negative in the front, and then we can actually do the integral here with a u substitution. This is just going to be u to the 1 half power du. And upon doing that integral, we get this. Well, let's see. It's 0. Oops. We're actually doing the integral now. So let's see. Well, since this is u to the 1/2, when you do the integral, you add 1 to 1/2 and you get 3/2. So you multiply by 2/3, and then you get 37 over 4 minus y to the 3/2 power. And we're going to take this from 0 to 9. All right, now all we have to do is plug in our upper and lower limits, in which case, well, let's see, we have negative 4/3 pi, and we're going to do, we're going to plug in the 9, so we're going to have 37 over 4 minus 9 to the power of 3/2 minus, and then we're going to have 37 over 4 minus 0 to the 3/2. And then all we have to do is work out this arithmetic here. Let's see. This is going to yield for us, let's see, it's going to be uh, pi, over, and then the 6. So we're going to get pi over 6 times uh, the square root, or 37, square roots of 37, minus 1. And that would be the area of that surface of revolution.